Everything we see in the universe, including ourselves, is ultimately made of atoms, tiny structures that act as the fundamental units of matter. But where did atoms originate? How did they first form? We know atoms are incredibly small, yet some scientists have even wondered whether the entire universe could, in some way, resemble a single vast atom. Picture an atom. At the center sits a compact core called the nucleus, and around it lightweight electrons zip around at astonishing speeds. This leads to a fascinating question. How do electrons keep circling the nucleus without losing energy and slowing down? This mystery puzzled physicists in the early 1900s and eventually pushed them into developing quantum mechanics. Researchers discovered that each atom contains a positively charged nucleus with most of its mass, while tiny negatively charged electrons occupy the surrounding space. With this basic structure in mind, early scientists attempted to build a more accurate atomic model. They first compared it to our solar system, imagining electrons orbiting the nucleus the way planets orbit the sun. But this comparison quickly fell apart. For one, accelerating charged particles emit electromagnetic radiation. Since electrons are both charged and constantly moving, they should lose energy, spiral inward, and collapse into the nucleus almost instantly. Yet atoms remain stable for billions of years. Clearly, something was missing. Another issue was that atoms emit radiation at very specific frequencies, not as a continuous spectrum, which contradicts what would happen if electrons orbited like planets. The puzzle deepened until Niels Bohr, a Danish physicist, introduced a revolutionary idea in 1913. In the early 20th century, the understanding of atomic structure underwent a revolutionary change thanks to the work of scientists like Niels Bohr and Max Planck. Before Bohr's contribution, the behavior of electrons around the nucleus was poorly understood. Classical physics suggested that electrons could orbit the nucleus at any distance and with any amount of energy, moving randomly like planets around the sun. However, this model failed to explain certain observed phenomena, especially the discrete lines in atomic spectra, specific wavelengths of light emitted or absorbed by atoms. Niels Bohr proposed a groundbreaking model in 1913 that challenged the classical view of electron motion. According to Bohr, electrons do not move randomly or occupy any arbitrary distance from the nucleus. Instead, they exist in fixed specific orbits or energy levels, which are quantized. This means that electrons can only reside in certain allowed orbits with defined energies and not anywhere in between. These orbits are stable, and electrons in them do not emit radiation, contrary to what classical physics predicted. Bohr also identified the smallest possible orbit, called the ground state, which an electron could occupy. It's impossible for the electron to spiral closer to the nucleus beyond this orbit. The essence of Bohr's model lies in the concept of quantization, a concept rooted in the earlier work of German physicist Max Planck. In 1900, Planck introduced the idea that energy is not continuous, but rather exists in discrete packets called quanta. Planck was studying blackbody radiation, the light emitted by heated objects, and found that classical physics couldn't explain the observed energy distribution. To resolve this, he proposed that energy could only be absorbed or emitted in fixed amounts proportional to the frequency of radiation. This proportionality constant is now called Planck's constant. Bohr took Planck's idea of quantization and applied it to the electron orbits in atoms. He suggested that the electron's angular momentum, the measure of its rotational motion around the nucleus. When an electron moves between these quantized orbits, it must absorb or emit energy equal to the difference between the initial and final orbit energies. This energy is released or absorbed as a photon of light, with a frequency directly related to the energy change. This explained why atoms emit or absorb light only at specific wavelengths, producing the characteristic spectral lines observed in experiments. Bohr's model was a major step forward because it successfully explained the spectral lines of hydrogen, the simplest atom, and introduced the quantum idea into atomic physics. It resolved problems classical physics couldn't, and laid the groundwork for the development of quantum mechanics, which would later provide a more complete and accurate description of atomic and subatomic systems. Bohr's atomic model, based on Planck's concept of energy quantization, showed that electrons occupy fixed orbits with quantized energies around the nucleus. This revolutionary idea marked the beginning of modern atomic physics and helped explain the discrete nature of atomic spectra, an essential milestone in our understanding of the microscopic world. Inspired by this, Bohr applied quantization to electron orbits. He argued that the smallest orbit carries exactly 1 unit of angular momentum, 1 times Planck's constant. Larger orbits would have multiples of this value, twice, 3 times, and so on, but never fractional amounts. This insight set the groundwork for a far more accurate picture of atomic structure and helped explain many mysteries surrounding electron behavior. To fully understand why electrons stay in defined orbits, though, quantum mechanics had to come into play. Electrons, and all particles, behave both like particles and waves. While we often picture an electron as a tiny object circling the nucleus, it can also be viewed as a wave surrounding it. And waves that are confined to a limited region cannot take on arbitrary shapes. They must form standing wave patterns that fit the space perfectly. Think of tightening a guitar string. Only certain wavelengths create clear musical notes. Similarly, an electron wave can only exist in patterns that fit neatly around the nucleus. The lowest allowed orbit corresponds to the simplest standing wave. As quantum theory improved, this model became more detailed, but the central idea stayed the same. Electrons cannot get arbitrarily close to the nucleus because quantum rules forbid them from occupying a smaller region. There's also a simpler explanation that avoids quantum mechanics. An electron is pulled toward the nucleus by electric attraction, but its motion gives it kinetic energy that pushes it outward. A stable orbit happens when these energies balance. The total energy of a bound electron is negative, meaning you'd have to add energy to pull it away, just like a planet orbiting the sun. Even though the electron is drawn inward, quantum rules ultimately prevent it from collapsing into the nucleus, allowing atoms to remain stable. Now let's explore how the very first atoms in the universe came into existence, a journey woven into the earliest moments of cosmic history. Everything in the cosmos, from microscopic dust to massive galaxies, is built from an unimaginable number of atoms, over 10 quadrillion vigintillion in the observable universe. These atoms contain electrons, protons, and neutrons, and inside those protons and neutrons exist even smaller components called quarks. The origins of these particles trace back to a dramatic event, the Big Bang. The Big Bang theory helps us understand how extreme energy at the birth of the universe transformed into matter and eventually atomic building blocks. But this is only the beginning of the story. Unpacking the details requires a deeper look into the universe's earliest eras. The exact moment when the universe began is still a mystery. Our most reliable cosmological model lets us trace back nearly to the start, to a point where theory predicts a singularity, an infinitely dense region where all matter and energy were compressed. But many scientists doubt whether this singularity physically existed. We can reliably examine the universe back to what's known as the Planck time, about 10 to the minus 43 seconds after the beginning. Earlier than this, physics as we know it simply doesn't apply, and the universe's first fraction of a moment remains hidden. To truly describe this era, scientists would need a complete quantum theory of gravity, one that merges gravity, which governs large-scale structures, with quantum mechanics, which governs tiny particles. This unknown era is called the Planck epoch. During this unimaginably early phase, it's believed that all fundamental forces, gravity, electromagnetism, the strong force, and the weak force, were unified into a single force. The universe expanded at a rate faster than the speed of light, not because objects were moving through space that fast, but because space itself was stretching. A region smaller than a subatomic particle ballooned to the size of an orange in a blink. This expansion erased any information about what came before it, making earlier events impossible to observe. Our most detailed understanding starts just after inflation, when the universe was unimaginably hot, dense, and rapidly expanding. From here, we can follow the sequence of events that eventually produced atoms. The universe's energy levels were still far beyond what we can recreate, but we believe gravity, the strong force, and the electroweak force, a combination of electromagnetic and weak forces, remained unified. Next came the emergence of the first elementary particles, likely around 10 to the minus 11th seconds. As temperatures dropped to around 10 to the 15th Kelvin, the quark epoch began. At this stage, the electroweak force split into separate electromagnetic and weak forces, a process known as electroweak symmetry breaking. The Higgs field gained its non-zero value and began giving mass to particles in the Standard Model. With these changes, the ingredients for future atoms appeared. The universe was now filled with a hot quark soup at around 1 quadrillion Kelvin. As expansion continued, temperatures fell to about 10 to the 12th Kelvin, around 10 to the minus 5th seconds, allowing quarks to combine into protons, neutrons, and certain mesons. The mesons later decayed into electrons and photons. Each drop in temperature triggered particle-antiparticle annihilation, creating bursts of photons and neutrinos. A tiny imbalance between matter and antimatter ensured that some quarks and electrons survived instead of being completely wiped out. These survivors became the building blocks of all future matter. By the 1 second mark, the universe reached the lepton epoch at around 5 billion Kelvin. Most particle-antiparticle pairs were gone, leaving behind a small but crucial number of protons, neutrons, and electrons, the essential components needed to form atoms. A few minutes later, Big Bang nucleosynthesis began, marking the next chapter in how the first atoms formed. Of the protons and neutrons formed in the early universe, the free neutrons were unstable and naturally decayed into protons through beta decay in roughly 10 to the minus 5 minutes. While the temperature remained extremely high, the conversion between neutrons and protons stayed in equilibrium. But as the universe continued to cool, neutron decay became more frequent. Free neutrons attempted to fuse with nearby hadrons to form larger nuclei before breaking down completely. Because of this, the early universe ended up with a composition that was roughly 75% hydrogen nuclei and about 25% helium-4 nuclei. Small quantities of deuterium, helium-3, and minute traces of lithium-9 also formed. As this cosmic evolution continued, the universe entered the photon epoch, a major phase lasting around 380,000 years. During this period, space was filled with free, positively charged nuclei, but they had no permanently attached electrons. The creation of stable neutral atoms required electrons to bind with nucleons, but the universe remained far too hot for this to happen. In the early stages of the universe, shortly after the Big Bang, conditions were extremely hot and dense. The universe was filled with a plasma, a state of matter consisting of free electrons, protons, which are the nuclei of hydrogen atoms, and other particles moving at incredibly high speeds. In this fiery, energetic environment, electrons and nuclei could not combine to form stable atoms because the intense thermal energy kept them separated. Whenever an electron came close to a nucleus, the enormous heat would cause the electron to be immediately knocked away. This constant repulsion prevented the formation of neutral atoms. This state created what is often called a cosmic fog. To understand why, we need to consider the behavior of photons, the particles of light and electromagnetic radiation. Photons are usually able to travel through space at the speed of light, allowing us to see objects around us and enabling energy to move across vast distances. However, in the early universe's plasma, photons could not travel freely. This was because they were constantly interacting with the free electrons and nuclei present in the plasma. When photons encounter free charged particles like electrons, they are scattered through a process called Thomson scattering. Each collision changes the direction of the photon, preventing it from moving in a straight line for any significant distance. Because the electrons and protons were so abundant and the universe was so dense, photons were scattered repeatedly and continuously. This meant that light could not propagate freely through the universe, but instead was trapped in a constant cycle of scattering events. This continuous scattering made the universe opaque, much like fog or smoke that obscures visibility on Earth. Just as foggy air scatters sunlight and prevents it from passing clearly, the early universe's plasma scattered photons so thoroughly that light was essentially trapped in a thick haze. This is why the term cosmic fog is used to describe this period. During this time, the universe was not transparent to light, and photons could not travel long distances without being deflected by particles. This foggy state persisted until the universe expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event is known as recombination, occurring roughly 380,000 years after the Big Bang. When neutral atoms formed, there were far fewer free-charged particles to scatter photons. Consequently, photons were finally able to travel freely through space without constant interruptions. This transition is referred to as the decoupling of matter and radiation. The photons that escaped at this time have been traveling ever since, gradually stretching to longer wavelengths due to the expansion of the universe. Today, we detect this ancient light as the cosmic microwave background, CMB radiation, a faint glow of microwaves filling the entire universe. The CMB provides a snapshot of the universe at the moment the cosmic fog lifted and the first neutral atoms formed, marking the beginning of the transparent universe we observe today. The early universe was a dense, hot plasma where electrons and nuclei were kept apart by intense thermal energy. This environment caused photons to scatter constantly, creating a cosmic fog that trapped light and prevented it from traveling freely. Only when the universe cooled enough for atoms to form did light finally escape, allowing the universe to become transparent and enabling the photons of the cosmic microwave background to journey through space to us. This foggy state persisted until the universe cooled to about 3000 Kelvin. At that temperature, electrons no longer had enough energy to escape the electromagnetic pull of nuclei. They finally formed stable, long-lasting bonds with them in a process known as recombination. With the birth of neutral atoms, the universe became transparent. Photons, now freed from constant scattering, could move through space without interruption. From our vantage point today, this moment is visible as the cosmic microwave background, CMB, the first light to travel across the universe. The CMB provides valuable clues about how the universe looked when the first atoms formed. From here, a deep question arises. Do atoms ever truly touch one another? To explore this, we must rethink what touching means at an atomic level. In everyday life, interaction is simple. If two magnets approach each other, or if two charged balloons come near, the forces between them represent direct interaction. These forces arise due to magnetic or electric properties, and we interpret this as the objects touching or influencing one another. But things become far stranger at the atomic scale. If we zoom down to atomic dimensions, we see particles in continuous motion, colliding, vibrating, and spinning in a chaotic dance. One crucial insight emerges: atoms have no solid outer surface. The nucleus sits at the center, made of protons and neutrons, while the electrons form a cloud of probability around it. According to quantum mechanics, an electron does not occupy a precise point. It exists as a spread-out wave of possible locations. These probabilities can mathematically extend across the entire universe, even though, in reality, electrons usually remain near the nucleus. Because atoms lack hard edges, they cannot physically touch the way solid objects do. But if we redefine touching as a strong interaction between particles, then atoms are constantly touching. Their interactions are driven by the electromagnetic force between their electrons and protons. This force technically has an infinite range, but it becomes meaningful only when atoms are close enough. When two atoms approach each other, their electron clouds repel each other, creating a force that prevents them from merging. This repulsion is the reason objects feel solid. For example, when a cup rests on a table, the electrons in the cup are repelled by the electrons in the table. Even though the atoms never physically meet, the electromagnetic repulsion is strong enough to oppose gravity, stopping the cup from falling through the table. However, atoms do not always repel each other. Sometimes the electromagnetic force causes attraction through the van der Waals force, which allows atoms to form bonds and create molecules. In molecules, the atoms are as close as they can be, effectively touching in the quantum sense. Atomic nuclei possess the ability to come into direct contact with one another, but this interaction requires extraordinarily extreme conditions due to the strong repulsive force between protons. Protons carry positive electric charges, and according to the principles of electromagnetism, like charges repel each other. This repulsion creates a significant barrier that prevents nuclei from approaching closely under everyday circumstances. The electromagnetic force acting between these positively charged protons is quite powerful and extends over relatively long distances compared to the forces that bind nuclei together internally. In typical environments, this repulsion keeps atomic nuclei separated, making direct contact or fusion highly unlikely. However, inside stars and other extreme cosmic environments, conditions change dramatically. The immense pressure and scorching temperatures in such places can supply the necessary energy to overcome the electromagnetic repulsion. When nuclei are pushed close enough together in these environments, a much stronger force, the nuclear strong force, comes into play. This force acts over very short distances, roughly the size of a proton or neutron, and can effectively pull the nuclei together once they are within this tiny range. As nuclei approach each other under these extreme conditions, the strong force binds protons and neutrons in neighboring nuclei, allowing them to merge into a single larger nucleus. This process is known as nuclear fusion. Fusion results in the release of an enormous amount of energy because the combined nucleus formed is more stable than the separate smaller nuclei. The difference in mass between the original nuclei and the fused nucleus is converted into energy according to Einstein's famous equation, E equals mc squared. Nuclear fusion is the fundamental energy source for stars, including our Sun. In the intense cores of stars, hydrogen nuclei protons collide with such energy that they overcome their mutual repulsion and fuse into helium nuclei. This reaction releases tremendous energy that powers the star, producing light and heat that can travel vast distances through space. This fusion process also creates heavier elements through subsequent reactions, contributing to the chemical complexity observed in the universe. Despite the strong electromagnetic repulsion, the interplay of forces under extreme conditions allows fusion to occur. The balance between the repulsive electromagnetic force and the attractive nuclear strong force is delicate and governs the stability and behavior of atomic nuclei. The strong force is incredibly powerful, but only effective over a very short range, so nuclei must be forced extremely close together for fusion to happen. Without the intense heat and pressure found in stellar cores or similar environments, this close approach would be impossible. However, when the environment is subjected to extraordinarily high pressure and temperature, such as those found in the cores of stars, nuclei can gain enough energy to overcome this repulsive force. In these intense conditions, nuclei move at very high speeds, increasing the likelihood that they will collide with sufficient force to come close enough for other forces to act. If two nuclei are brought near enough and remain in close proximity for even a very brief period, a much stronger force called the strong nuclear force comes into play. Unlike the electromagnetic force, the strong nuclear force is attractive and acts only at very short distances, binding protons and neutrons tightly together within a nucleus. When the nuclei overcome their electromagnetic repulsion and get close enough for the strong force to dominate, they can fuse together to form a larger nucleus. This fusion process releases an enormous amount of energy because the mass of the resulting nucleus is slightly less than the sum of the masses of the original nuclei, with the lost mass converted into energy according to Einstein's equation. This energy release is what powers stars like our Sun, providing the heat and light that sustain life on Earth. In the Sun, for example, hydrogen nuclei, protons, fuse to create helium through a series of reactions known as the proton-proton chain. The immense gravitational forces in the Sun's core create the necessary pressure and temperature, causing the protons to collide at extremely high speeds, overcome their mutual repulsion, and fuse. The energy produced during fusion counteracts the Sun's gravitational collapse and radiates outward, ultimately reaching us as sunlight. This process not only powers the Sun, but also leads to the creation of heavier elements over time, driving the life cycles of stars and contributing to the chemical complexity of the universe. While the fusion of nuclei requires conditions far beyond anything found on Earth's surface, it illustrates the delicate balance between forces in nature. The electromagnetic force works to keep positively charged particles apart, while the strong nuclear force can pull them together when the right circumstances arise. This interplay governs the behavior of matter at the smallest scales and fuels the stars that illuminate our cosmos. Next comes another fascinating idea. Are two atoms of the same element truly identical? In most cases, they are not. Even if two atoms belong to the same element, their electrons may be in different energy states. A copper atom with an excited electron behaves differently from a copper atom in its ground state. Excited atoms emit light when their electrons drop back down, while identical atoms in the lowest state do not. Chemical reactions depend heavily on electron states, so atoms of the same element can react differently. Even when electron states match, atoms might move or rotate at different speeds. An atom in a slow, stable state, such as in a solid, can form strong bonds, while the same atom moving rapidly in a gas cannot. Even if two atoms have identical electron configurations and similar motion, they can still differ because the nucleus itself can exist in different internal states. Protons and neutrons can be excited, and the entire nucleus can rotate or vibrate in multiple ways. Two atoms of gold, for example, might behave differently in nuclear reactions due to differences in their nuclear energy states. Isotopes add another layer. Atoms of the same element can contain different numbers of neutrons and still be chemically identical. But in nuclear reactions, isotopes behave very differently. Some decay quickly, others remain stable for billions of years. Carbon-12 and carbon-14, for instance, are both carbons, but carbon-14 is radioactive and used in radiocarbon dating. In short, achieving two perfectly identical atoms is nearly impossible unless every electronic, atomic, and nuclear property matches exactly. But when all these states are truly identical, the atoms become indistinguishable and have no unique identity of their own. This leads to another question. Do atoms have color? You see color on screens, fabrics, and objects made of atoms, so does each atom have a color of its own? The answer is no. Color is a perceptual experience created by the brain, not a physical property of a single atom. Light is made of photons, which behave as particles when observed, but act like waves when unobserved, a phenomenon called wave-particle duality. These waves come in different frequencies, forming a vast spectrum from radio waves, as large as planets, to gamma rays, smaller than atoms. Human eyes detect only a tiny slice called visible light. Early vision evolved underwater, and visible light happens to pass easily through water, unlike ultraviolet or infrared light. On a different world, say around a neutron star, life might develop eyes that see X-rays instead. When light encounters material, atoms either absorb certain wavelengths or reflect them. A blue cloth looks blue because it reflects blue wavelengths while absorbing the rest. Black objects absorb nearly all wavelengths and therefore heat up faster. while white objects reflect most of the light. This is known as bulk reflection. But a single atom is far too small for visible light to interact with in this way. Light's wavelength is vastly larger than an atom, so individual atoms cannot reflect or absorb light in a way that would produce a color. Thus, atoms themselves have no color. Color emerges only when vast groups of atoms interact collectively with light. When we observe thermal radiation, a fascinating phenomenon unfolds. Thermal radiation is the light or electromagnetic radiation emitted by a material as it heats up. As the temperature of the material rises, the atoms and molecules within it begin to move more rapidly, vibrating and colliding with greater intensity. This increased motion causes these particles to emit photons, tiny packets of light energy. These photons carry energy away from the material in the form of electromagnetic waves, which can be detected as visible light or other types of radiation depending on the temperature. What's truly intriguing about thermal radiation is that the light emitted by different materials at the same temperature follows a remarkably consistent pattern. This means that whether you heat a piece of metal, a chunk of wood, or a lump of coal, the color of the light they emit at a given temperature will be very similar. Initially, as the temperature begins to rise, the material might glow with a faint red light. As it gets hotter, the light shifts through orange, yellow, and eventually white, with higher temperatures producing blue or even ultraviolet radiation. This sequence of colors is known as a blackbody radiation spectrum, and it depends only on the temperature of the material, not on its composition. This uniform behavior puzzled scientists for many years because the expectation was that different materials would emit light differently depending on their unique atomic structures. However, the explanation lies in the fact that thermal radiation arises from the collective behavior of a large number of particles, not from individual atoms. When a vast number of atoms or molecules are packed together, their motions and electromagnetic interactions combine to produce a smooth, continuous spectrum of light. This collective emission is what gives rise to the predictable pattern of colors in thermal radiation. By contrast, a single isolated atom behaves quite differently. An individual atom can emit light, but only at very specific wavelengths, producing what are called spectral lines rather than a continuous spectrum. These spectral lines correspond to electrons jumping between discrete energy levels within the atom, releasing photons of precise energies. However, when heated, a single atom does not emit the broad, continuous glow of thermal radiation because it lacks the complex interactions with neighboring atoms and the wide range of vibrational motions that occur in a bulk material. The glowing effect we see when materials are heated is not just a simple property of individual atoms or particles. Rather, it is a complex phenomenon that emerges from the collective behavior of countless particles working together. When a material is heated, the atoms and molecules inside it begin to vibrate and move more vigorously. These movements cause the particles to emit light in the form of photons. However, a single atom on its own does not emit this kind of light in a way we can easily detect. Instead, it is the combined activity of many atoms that produces the smooth and continuous glow we observe. This collective emission of light results in what is known as thermal radiation. Thermal radiation has a very characteristic pattern of colors, often described as a gradient that changes smoothly from red to orange, yellow, white, and even blue, depending on the temperature of the material. This pattern is not random. It follows a specific distribution called the blackbody radiation spectrum. A blackbody is an idealized object that absorbs all radiation that falls on it and then emits radiation purely based on its temperature. Real objects approximate this behavior, and their emitted light closely follows the blackbody spectrum. Understanding this pattern of thermal radiation was a major scientific challenge at the end of the 19th century. Classical physics, which worked well to explain many other phenomena, failed to predict the observed blackbody radiation spectrum correctly. According to classical theories, the intensity of emitted radiation should increase indefinitely at shorter wavelengths, leading to what was known as the ultraviolet catastrophe. This paradox puzzled scientists and suggested that something fundamental about energy and light was not yet understood. The breakthrough came from Max Planck, a German physicist who studied the problem carefully. Planck proposed a bold and revolutionary idea. Energy is not emitted or absorbed continuously, but rather in discrete tiny packets called quanta. This means that atoms and molecules emit or absorb energy only in specific amounts determined by a fundamental constant, now called Planck's constant. This quantization of energy explained why the blackbody radiation spectrum has the shape it does, and avoided the ultraviolet catastrophe predicted by classical physics. Planck's discovery was the seed that grew into the entire field of quantum mechanics, which fundamentally changed our understanding of the microscopic world. It introduced the concept that energy, light, and matter have properties that are quantized and that classical continuous models could not fully explain. The glowing effect in heated materials is a macroscopic outcome of many particles acting together, producing the continuous spectrum of thermal radiation that follows a precise pattern called the blackbody radiation spectrum. Attempts to explain this phenomenon led Max Planck to propose that energy is quantized, a groundbreaking idea that became the cornerstone of quantum physics. This insight transformed science by providing a deeper, more accurate understanding of the behavior of energy and matter at the smallest scales, shaping modern physics as we know it today. Thermoradiation is the emission of light caused by the increased motion of atoms and molecules in a material as it heats up. Despite differences in material composition, all heated substances emit light with a similar colors pattern because this effect arises from the collective behavior of large groups of particles. A single atom, on its own, cannot produce the continuous glow characteristic of thermal radiation, highlighting the remarkable difference between microscopic atomic behavior and the macroscopic properties we observe in everyday life. Now let's shift to gas discharge. When electricity passes through a collection of atoms, the atoms become energized and begin releasing photons in response. The colors produced depend entirely on the substance, creating a unique emission spectrum for each element. Hydrogen, for instance, emits specific colors that differ from those of iron. In this way, every element carries its own pattern of emitted light, a kind of color signature defined by its spectrum. But while we often treat this as the colors of an element, it doesn't apply in the everyday sense. Atoms are far smaller than the wavelength of visible light, so they cannot possess colors the way large objects do. Colors, as we perceive it, simply doesn't exist at the atomic scale. Next, let's examine a puzzling question. Why don't the protons inside a nucleus push each other apart? Nature operates through four basic forces: gravity, electromagnetism, the weak force, and the strong force. On everyday scales, we're familiar with gravity, but inside atoms the other three dominate. Electromagnetism, which is enormously stronger than gravity, pulls electrons toward protons, but it also causes like charges, such as two protons, to repel. By Coulomb's law, two protons in a helium nucleus should repel each other so strongly that the nucleus would tear itself apart instantly. Yet in reality, the protons stay bound together. The reason is the strong nuclear force, a force roughly 100 times stronger than electromagnetism, acting only over extremely short distances within the nucleus. Although it behaves very differently from electromagnetism, it is the dominant force holding the nucleus together. Quantum chromodynamics, QCD, helps explain how this works. Inside protons and neutrons are quarks, tiny constituents of matter, and gluons, which carry the strong force. A proton contains two up quarks and one down quark. A neutron contains two down quarks and one up quark. Gluons interact with quarks through an unusual type of colors charge, unrelated to visual colors. These charges come in red, green, and blue, combining to form a neutral white state. Neutrality can be achieved either through all three colors together or through colors and anticolors pairs. The gluon-quark interaction binds these particles tightly inside nucleons. Only quarks and gluons feel the strong force, with gluons playing a role similar to photons in electromagnetism. They act as carriers of force. As quarks attempt to move apart, the force between them behaves like a stretched rubber band. Trying to pull a quark out supplies enough energy to create a new quark-antiquark pair, forming what's called a meson. This mechanism prevents quarks from ever existing freely. They are always confined with at least one partner. Mesons are also central to understanding how protons and neutrons interact inside nuclei. Although weaker than the force-binding quarks within a nucleon, the nuclear strong force between nucleons is still powerful enough to overcome the electrostatic repulsion between protons. It acts only over extremely short distances, roughly the size of a proton, and decreases sharply as particles move farther apart. This limitation plays an important role in determining how large a stable nucleus can be. The nuclear strong force, mediated by mesons, locks protons and neutrons together inside atoms. It works in harmony with the strong force inside nucleons, which binds quarks together. Understanding these interactions is essential for grasping the nature of matter and the existence of everything around us. Now let's focus on the size of a proton, one of the essential features of subatomic physics. Although we often assume that atomic properties are well understood, a surprising discovery in 2010 challenged long-held measurements of proton size. This experiment produced a noticeably different value from what had been widely accepted, initiating a decade of investigation into what became known as the proton radius puzzle. Before exploring what scientists uncovered, it's important to discard the idea of a proton as a smooth, solid sphere. A proton is better described as a swirling cloud of quarks held together by gluons. It is the distribution of positive charge within this cloud that gives the proton its effective radius. For many years, physicists relied on two primary methods to determine this radius. The first method involved firing electrons at atoms, usually hydrogen, which has only one proton and one electron. By analyzing how electrons scatter off the proton, researchers could determine where its positive charge begins to fade, marking the outer boundary of the proton. The second method measured the energy needed to move hydrogen's electron from one energy state to another. Since the electron occasionally resides within the proton during this motion, a larger proton would weaken the electrical attraction slightly, changing the energy required for transitions. Thus, the proton's size could be inferred from these energy levels. For decades, both methods pointed to a proton radius of about 0.876 femtometers. But around 2010, a new approach dramatically shifted this understanding. Instead of using electrons, researchers studied hydrogen in which the electron was replaced by a muon, a particle similar to an electron but 207 times heavier. This extra mass pulls the muon much closer to the proton, making it far more sensitive to the proton's size. The results were stunning. The proton measured in muonic hydrogen appeared about 4% smaller than the earlier value. This discrepancy led many to wonder whether new physics or even unknown particles might be involved. In September 2019, scientists at York University revisited an important question in physics. What is the true size of the proton? For many years, physicists had debated the exact radius of this fundamental particle which forms the core of every atom's nucleus. The proton radius is incredibly tiny, on the order of femtometers or quadrillionths of a meter, and measuring it accurately is a formidable challenge. However, precise knowledge of the proton's size is crucial because it influences our understanding of atomic structure and the fundamental forces that govern matter. Before the York University experiment, there was a puzzling discrepancy known as the proton radius puzzle. Measurements using traditional methods, such as electron scattering and spectroscopy of ordinary hydrogen atoms, had produced one value for the proton radius, about 0.88 femtometers. However, a newer, more precise technique involving muonic hydrogen suggested a smaller radius, around 0.84 femtometers. Muonic hydrogen is an exotic atom where the usual electron is replaced by a muon, a particle similar to the electron but much heavier. Because muons orbit closer to the proton due to their greater mass, scientists expected this method to give a more precise measurement. Yet the results conflicted with those from ordinary hydrogen, raising questions and speculation about whether new physics beyond the standard model might be involved. To address this discrepancy, researchers at York University used a cutting-edge technique called frequency offset separated oscillatory fields. This advanced method allows extremely precise measurements of the energy levels of ordinary hydrogen atoms. Essentially, by carefully analyzing the frequencies at which electrons transition between energy states in hydrogen, scientists can infer details about the size of the proton they orbit. This technique improves upon earlier methods by reducing sources of error and increasing the accuracy of the measurements. When York University scientists applied this technique to ordinary hydrogen, their results closely matched the measurements obtained from muonic hydrogen. Both pointed to a proton radius of approximately 0.833 femtometers, smaller than what earlier experiments had suggested. This convergence of findings was significant because it indicated that the previously larger proton radius values likely stemmed from experimental errors or limitations rather than a need for new physics. The importance of this result cannot be overstated. It effectively resolved a decade-long mystery by showing that the proton radius puzzle was not due to some exotic, unknown phenomena, but rather the natural challenges of making ultra-precise measurements at such a tiny scale. The consistency between the new ordinary hydrogen measurements and the muonic hydrogen measurements restored confidence in our current understanding of atomic physics and the Standard Model. The York University experiment in 2019 used an advanced measurement technique to precisely determine the size of the proton in ordinary hydrogen atoms. Their findings agreed with the earlier muonic hydrogen results, both indicating a proton radius of about 0.833 femtometers. This agreement suggested that the previous discrepancies were likely due to measurement errors, not new physical effects, thereby helping to resolve a significant scientific puzzle and reaffirming our foundational understanding of atomic structure. To better grasp why atoms seem contradictory, mostly empty space yet forming solid objects, consider a thought experiment. Imagine enlarging a tabletop 1 billion times until its atoms are the size of melons. Even at this scale, the nucleus in the center would remain tiny and invisible, as would the electrons around it. Given all this empty space, why don't objects pass through each other? And why doesn't light slip through the gaps between atoms? The answer lies in the complex behavior of electrons inside atoms. Unlike planets orbiting a star, electrons do not follow neat circular paths. Instead, they behave more like a rapidly shifting cloud, similar to a swarm of birds or bees that moves too quickly to track individually. Although it seems chaotic, this collective motion forms well-defined patterns dictated by Schrödinger's equations. These patterns act like dance steps. Some are smooth and slow, like a waltz. Others are quick and energetic, like a Charleston. Every electron follows one of these allowed patterns, and the Pauli exclusion principle ensures that no two electrons in the same atom share the exact same step. This perspective helps explain why matter feels solid. Electrons must obey their specific patterns, and changing from one pattern to another requires energy. When electrons absorb light, they jump to faster, more energetic steps. When they release energy, they drop to slower ones, often emitting light in the process. So when a beam of light tries to move through a solid object like a table, the electrons absorb part of the light's energy and then re-emit it. This constant absorption and re-emission prevents light from passing through freely. The combination of reflected and absorbed light produces the colors and textures we see, while the behavior of these electron patterns creates the sensation of solidity. When we observe thermal radiation, we encounter a phenomenon that reveals much about the nature of matter and energy. When a material is heated,
the atoms and molecules inside it start to vibrate and move more energetically. This increase in internal motion causes these particles to emit light in the form of photons. This emission of light due to heat is what we commonly recognize as glowing, such as the red or orange glow of heated metal or the warm light from a fire.
What is especially intriguing about thermal radiation is that the colors of the emitted light follows a specific and predictable pattern regardless of the material being heated. Whether it's a piece of iron, a lump of coal, or a candle flame, the glow progresses through a spectrum of colors as the temperature rises. At lower temperatures, the glow appears reddish because the emitted photons have lower energy and longer wavelengths. As the temperature increases, the colors shifts to orange, yellow, white, and eventually blue at very high temperatures, corresponding to photons with higher energies and shorter wavelengths. This pattern is not random. It follows a well-defined curve known as the blackbody radiation spectrum. A blackbody is an idealized object that absorbs all radiation falling on it and re-emits energy solely based on its temperature. Real objects approximate this behavior closely enough for their thermal emission to be described by the blackbody radiation curve. This spectrum is smooth and continuous, showing how the intensity of emitted light varies with wavelength for a given temperature. The remarkable universality of this pattern means that thermal radiation does not depend on the chemical makeup of the material, but only on its temperature. An important aspect of this phenomenon is that it requires the collective action of a large number of atoms or molecules. A single atom, isolated in space, does not emit this continuous glow when heated. Instead, individual atoms produce very specific colors or wavelengths of light related to electron transitions. But these emissions are distinct and limited, not the smooth spectrum associated with thermal radiation. The thermal glow that we see comes from the complex interactions between countless particles vibrating together, creating a combined effect that produces the familiar glowing colors. This collective nature of thermal radiation is crucial because it ties into how energy is distributed and exchanged in matter. The atom's vibrations cause their electrons to move and oscillate, and these oscillations generate electromagnetic waves, in other words, light. The energy distribution of these waves shifts with temperature, which is why the colors changes as the material gets hotter. Understanding thermal radiation was a key step in the development of modern physics. Classical physics struggled to explain the observed blackbody spectrum, especially at shorter wavelengths. It was the work of Max Planck who introduced the idea that energy is quantized and emitted in discrete packets called quanta that resolved this problem. This insight laid the foundation for quantum mechanics, a field that fundamentally changed our understanding of the microscopic world. Thermoradiation is a fascinating effect that arises from the collective vibrations of atoms in heated materials. The emitted light follows a consistent pattern of colors, independent of the material itself, and only emerges from the combined action of many particles. This phenomenon not only explains everyday glowing objects, but also played a critical role in the birth of quantum physics. Now shift the focus to gas discharge. When an electric current passes through a gas, the atoms inside absorb energy and respond by emitting light. Each element produces its own unique set of colors, forming a distinctive emission spectrum. Hydrogen, for example, generates specific wavelengths different from iron or helium. Every element, therefore, carries its own spectral fingerprint, like a unique optical signature. But this colors is not colors in the everyday sense, because atoms are far smaller than the wavelengths of visible light. An atom cannot possess colors the way macroscopic objects do. Colors, as we perceive it, simply has no meaning at atomic scales. Next, consider a fundamental question. Why don't the protons inside a nucleus violently push away from one another? Nature is governed by four basic forces: gravity, electromagnetism, the weak force, and the strong force. In daily life, gravity dominates our experience, but at the atomic level, the electromagnetic weak and strong forces control everything. Electromagnetism, which is vastly stronger than gravity, attracts electrons to protons, but also causes like charges, such as two protons, to repel each other with enormous force. According to Coulomb's law, two protons inside a helium nucleus should repel so strongly that the nucleus should explode apart instantly. Yet that does not happen. The reason is the strong nuclear force, a force about 100 times stronger than electromagnetic repulsion, operating only over extremely tiny distances inside atomic nuclei. Though it behaves very differently from electromagnetism, it overwhelmingly dominates at these scales, binding protons tightly together. Quantum chromodynamics, QCD, provides the framework to understand how this happens. Protons and neutrons contain quarks, the smallest known constituents of matter, along with gluons, which transmit the strong force. A proton contains two up quarks and one down quark, while a neutron holds two down quarks and one up quark. Gluons interact with quarks through a special type of colors charge, unrelated to visible colors. The three colors charges, red, green, and blue, combine to make a neutral or white particle. Neutrality can arise either from all three colors together or from a color paired with its anticolors. The interaction between gluons and quarks binds these particles tightly within nucleons. Only quarks and gluons feel the strong force, with gluons functioning somewhat like photons do in electromagnetism as carriers of force. But unlike electromagnetism, the strong force becomes stronger as quarks try to pull apart. It behaves like a stretched rubber band. The farther the quarks move, the stronger the force becomes. Attempting to separate a quark injects enough energy into the system to create a new quark-antiquark pair, forming a meson. This process ensures that quarks are never observed alone. They remain permanently confined within composite particles. Mesons are fundamental particles that play a vital role in holding atomic nuclei together. Inside the nucleus of an atom, protons and neutrons, collectively known as nucleons, are packed closely. While the protons are positively charged and naturally repel each other due to electromagnetic forces, they remain bound tightly together along with neutrons. This stability is largely thanks to the nuclear strong force, a powerful interaction mediated by mesons. The nuclear strong force is distinct from the force that holds quarks together inside individual protons and neutrons. Inside nucleons, quarks are bound by the fundamental strong interaction, often referred to as the colors force, which is the strongest force in nature. However, this quark-binding force acts at an even smaller scale, inside each proton or neutron. The force that acts between entire nucleons, the nuclear strong force, is somewhat weaker but still incredibly strong compared to electromagnetic repulsion. Mesons serve as the carriers or messengers of this nuclear strong force between protons and neutrons. You can think of mesons as particles exchanged back and forth between nucleons, creating an attractive force that overcomes the electrical push, trying to separate the positively charged protons. This exchange is similar to how photons carry electromagnetic forces, but mesons are much heavier, which limits the range over which they can act. This nuclear force has a very short range, roughly the size of a proton, which is about 1 femtometer, 1 quadrillionth of a meter. When nucleons come within this tiny distance, the nuclear strong force becomes dominant, effectively binding them together into a stable nucleus. However, if nucleons are pushed further apart beyond this range, the force rapidly diminishes and becomes too weak to hold the nucleus intact. This limited reach of the nuclear strong force helps explain why atomic nuclei can only grow so large while remaining stable. As the number of protons increases in heavier elements, the electromagnetic repulsion between the many positively charged protons grows stronger. Although the nuclear strong force continues to act, it only influences nucleons that are very close together. Eventually, in very large nuclei, the repulsive forces start to dominate because the nuclear force cannot effectively bind nucleons that are farther apart. This is why elements with very high atomic numbers tend to have unstable nuclei that decay or break apart over time. The role of mesons in this binding process was first proposed by physicist Hideki Yukawa in the 1930s. He predicted the existence of mesons as force carriers, which was later confirmed experimentally. This discovery was a major milestone in nuclear physics, deepening our understanding of how atomic nuclei remain intact despite the repulsive forces present. Mesons mediate the nuclear strong force that binds protons and neutrons within atomic nuclei. Though weaker than the fundamental strong force holding quarks inside nucleons, this nuclear force is still powerful enough to overcome electromagnetic repulsion among protons. Its short-range nature, limited to distances about the size of a proton, determines the maximum size of stable nuclei. Without mesons and the nuclear strong force, the atomic nucleus as we know it would not exist, and the vast diversity of elements in the universe would be impossible. The meson-mediated nuclear force locks protons and neutrons in place, holding atomic nuclei together. It works alongside the internal strong force, which binds quarks into protons and neutrons. Understanding how these forces cooperate is essential for explaining the stability of matter and the structure of everything in the physical universe. Now let's explore the size of a proton, one of the most fundamental and surprising questions in modern physics. Although we often assume that proton properties are well established, a startling discovery in 2010 challenged the long-accepted measurements of proton radius. That experiment revealed a noticeably smaller value than previously believed, triggering a decade-long scientific investigation known as the proton radius puzzle. Before diving into the puzzle, we must discard the outdated image of a proton as a smooth, rigid sphere. In reality, a proton is a turbulent, dynamic cloud of quarks and gluons. The spatial distribution of its positive charge defines its effective size, not a solid surface. Physicists traditionally use two main methods to measure the proton's radius. The first method involved scattering electrons off hydrogen atoms, ideal for study because hydrogen contains just one proton and one electron. By analyzing how electrons bounce off the proton, scientists could determine where the proton's electric field begins to weaken, indicating the boundary of its charge distribution. The second method relied on measuring the energy needed for an electron in hydrogen to move between different energy levels. Since the electron sometimes enters the region occupied by the proton, a larger proton weakens the electric attraction slightly. This alters the energy required for these transitions, allowing researchers to infer the proton's size. In 2019, a highly precise experiment at York University remeasured regular hydrogen using an advanced technique known as frequency offset separated oscillatory fields. This experiment produced a radius of 0.833 femtometers, consistent with the monic hydrogen measurement. The mystery was resolved. Earlier experiments had inaccuracies, and no exotic new physics was required. To grasp the seemingly paradoxical nature of atoms, where most of their volume is empty space, it helps to consider a useful analogy. Imagine enlarging a table by a factor of 1 billion, so that the atoms become the size of melons. Despite this immense scale-up, the atomic nucleus remains tiny and barely visible at the center, and the electrons, moving rapidly around it, are still elusive. This raises the question, if atoms are mostly empty space, why can't objects pass through one another? Why does light not simply travel unimpeded through the gaps between atoms? The answer lies in the behavior of electrons within atoms. The simple picture of electrons orbiting the nucleus like planets circling the sun is misleading. Instead, electrons form a dynamic, swirling cloud that moves unpredictably. Similar to a swarm of bees or flock of birds, individual electron paths are impossible to track precisely, but their collective motion follows well-defined patterns described by quantum mechanics. These patterns, or electron orbitals, are governed by Schrödinger's equations, which predict the probabilities of where electrons are likely to be found. The electron dance is not random, but constrained to specific energy states. Some patterns resemble smooth, flowing waltzes, while others are rapid, energetic dances. Crucially, the Pauli exclusion principle prevents any two electrons in an atom from occupying the exact same quantum state, ensuring a complex but ordered electron configuration. When light tries to pass through a material such as a table, the electrons in the atoms absorb photons, temporarily raising their energy states. After a brief time, the electrons release this energy, often emitting light again. This continuous cycle of absorption and emission causes the light to be reflected or scattered, which is why the table appears opaque and solid rather than transparent. But what about the physical sensation of solidity? Why does the table resist being pushed or penetrated? When your finger presses on the table, the electrons in the atoms of your skin come extremely close to the electrons in the table's atoms. According to quantum rules, an electron in a lower energy state near one nucleus cannot simply move to the same state near another nucleus if it's already occupied. Therefore, the electrons must shift into higher, unoccupied energy states, which requires energy. This energy demand creates a powerful repulsive force. Bringing all the atoms in your finger close enough to those in the table to merge would require pushing electrons into these higher energy configurations across both sets of atoms, a process requiring far more energy than your muscles can exert. This resistance manifests as the sensation of hardness or solidity when touching the table. Moving on, consider why atoms bond to form molecules. Though there are fewer than 100 naturally occurring elements, the variety of chemical compounds and materials we observe is immense. This diversity arises because atoms rarely exist alone. They combine to form molecules. Atoms have a natural tendency to bond with one another because they seek to achieve a state of lower total energy. This tendency is fundamental to chemistry and is the driving force behind the formation of molecules. To better understand this, imagine a marble placed at the top of a hill. Just as the marble naturally rolls downhill to reach the lowest possible point, atoms roll toward bonding arrangements that minimize their total energy. This tendency toward energy minimization is what governs the behavior of atoms and the formation of the complex structures we observe in nature, ranging from the very air we breathe to the intricate molecules inside living organisms. Atoms are made up of a positively charged nucleus surrounded by negatively charged electrons. The way these electrons are arranged around the nucleus determines how atoms interact with one another. Atoms tend to be more stable when their outermost electron shells are either full or satisfy a particular configuration that minimizes the energy of the system. Most atoms do not have full outer shells by themselves, so they achieve stability by bonding with other atoms. This bonding allows them to either share electrons, as in covalent bonds, or transfer electrons, as in ionic bonds. Both processes help atoms reach a lower energy state and achieve a more stable electronic configuration. Take oxygen, for example. A single oxygen atom has 6 electrons in its outer shell but needs 8 to be stable. Rather than existing alone, oxygen atoms tend to pair up to form O2 molecules. In doing so, the 2 oxygen atoms share electrons, filling their outer shells more completely and lowering their combined energy. Similarly, nitrogen atoms pair to form N2 molecules, sharing electrons to satisfy their outer shell requirements. Water, H2O, is another classic example. Here, 2 hydrogen atoms bond with 1 oxygen atom. The sharing of electrons between hydrogen and oxygen creates a molecule with a lower total energy than the individual atoms alone. This drive to reach lower energy states explains why atoms prefer to form molecules rather than exist in isolation. When atoms bond, the system's overall energy decreases, creating a more stable state. The new molecular structures that emerge from these bonds often have properties quite different from those of the individual atoms. This explains why water behaves very differently from isolated hydrogen or oxygen atoms, and why oxygen in molecular form supports life by enabling respiration, rather than in atomic form. The process of bonding and energy minimization is governed by the principles of quantum mechanics, which describe how electrons behave in atoms and molecules. When atoms approach each other, their electron clouds interact, and the electrons adjust their positions to create a more stable arrangement. The sharing or transfer of electrons results in a net decrease in the potential energy of the system. This energy change is what makes bonding favorable. Overall, the natural tendency of atoms to bond arises from their quest to lower their total energy. This fundamental principle shapes the vast variety of molecules that exist in the universe, from simple gases like oxygen and nitrogen to complex organic compounds vital to life. The stability and diversity of the chemical world are thus rooted in this simple yet profound drive of atoms seeking the lowest possible energy states through bonding. At the quantum level, bonding involves a subtle interplay between the negatively charged electrons that repel each other and the positively charged nuclei that attract electrons. When two hydrogen atoms approach each other, their electrons repel, but the protons in each nucleus attract the other atom's electrons, creating a balance. At a particular optimal distance, the atoms share electrons in a way that lowers the system's total energy, stabilizing the molecule. This shared electron pair forms a covalent bond, a kind of quantum dance partnership between atoms. The overall stability of molecules depends on the arrangement of electrons in their atomic orbitals, which follows quantum mechanical principles such as the Pauli exclusion principle and Schrödinger's equation. These principles explain the magic numbers of electrons, 2, 10, 18, 36, 54, and 86, that correspond to especially stable electron shells, as seen in noble gases. Atoms seek to fill their outermost shells, achieving maximum stability by either sharing electrons, covalent bonds, or transferring electrons, ionic bonds. The intricate balance between attractive and repulsive forces in electron clouds and nuclei governs these bonding behaviors. In larger molecules like water, the calculations become more complex. Models such as the Morse potential help approximate bond lengths and energies to predict molecular stability. Quantum mechanics thus provides a powerful framework for understanding how atoms interact and why molecules form, illuminating the underlying order in nature's complexity. However, while it explains the how, quantum mechanics does not fully answer why these laws govern existence itself. Turning to an astronomical scale, neutron stars present a fascinating question. Can they be thought of as gigantic atomic nuclei? Neutron stars are among the densest objects in the universe, essentially massive nuclei spanning kilometers in diameter. Their existence challenges our understanding of matter and forces. Inside a star, a delicate balance exists between gravity pulling matter inward and radiation pressure from nuclear fusion pushing outward. As hydrogen fuses into helium and later into heavier elements like carbon, oxygen, and silicon, the core builds layers of increasingly heavy nuclei. Eventually, fusion ceases when iron, which cannot release energy by fusion, accumulates. If the core's mass exceeds about 1.4 times that of the Sun, gravity overwhelms the pressure and the star collapses catastrophically. At this point, fundamental forces inside atoms resist further collapse. The weak force causes protons and neutrons to interchange identities in the extreme environment, converting protons into neutrons and vice versa. This particle freeze-out happens when the universe cools to about 1 second old, fixing the ratio of protons to neutrons. Down quarks, which make up neutrons, are heavier than up quarks in protons, so neutrons are slightly heavier. This mass difference causes an imbalance in neutron and proton numbers, roughly 7 protons for every neutron, profoundly influencing the universe's formation. This delicate balance between protons and neutrons shapes the nature of atomic nuclei throughout the universe. Neutron stars, in essence, are massive collections of neutrons packed together so densely that they behave almost like a giant atomic nucleus on a cosmic scale. In these stars, the gravity is so intense that electrons combine with protons to form neutrons, leaving behind an ultra-dense core composed mostly of neutrons. The pressure from the strong nuclear force, the same force that binds quarks inside protons and neutrons and holds protons and neutrons within nuclei, now acts on a much larger scale to prevent the star from collapsing further into a black hole. Understanding neutron stars requires not only knowledge of the fundamental forces, but also insights from quantum mechanics and nuclear physics. The physics governing these extreme objects ties together the tiniest building blocks of matter with the largest scales of astrophysics. This fascinating connection highlights how the fundamental forces and particles studied in atomic physics have implications far beyond our everyday world, influencing the behavior of stars, galaxies, and the evolution of the cosmos itself. Protons form the cornerstone of hydrogen and helium, the essential fuels of stars and the building blocks for all heavier elements in the universe. Their abundance relative to neutrons enables the complex interactions that underpin chemistry and biology. Had the initial conditions been slightly different, if, for instance, the down quark possessed a marginally lower mass during the universe's fine-tuning, the cosmos we observe today would be fundamentally altered. If neutrons were lighter than protons, they would have dominated during the freeze-out phase, leading to a universe rich in uncharged neutrons but scarce in protons. Such a shift would drastically limit chemical diversity. Hydrogen atoms consisting of a single proton without neutrons would be unstable and short-lived. Some heavier protons might have survived by pairing with neutrons to form helium, yet helium's characteristic chemical inertness would stifle further reactions. With an overabundance of inert neutrons, nuclear fusion would struggle to proceed, leaving behind a cold, dark void, devoid of stars, galaxies, planets, and certainly life as we understand it. Thus, we owe a profound debt of gratitude to the universe's unexplained preference for protons over neutrons. But this is not the only asymmetry embedded in the cosmos during its early evolution. Another mysterious and fortunate imbalance is the near absence of antimatter. Looking skyward, we might imagine an alien civilization self-destructing, not with the dramatic flare of a supernova, but through the silent annihilation unleashed by antimatter weapons. Throughout Earth's history, conflicts fueled by territorial disputes and discord have been all too common, and it is reasonable to expect similar strife elsewhere in the galaxy. On a hostile alien world with advanced technology surpassing ours, the harnessing of antimatter could lead to devastating consequences. These extraterrestrials might manufacture and store antimatter, suspending it in vacuum chambers using electromagnetic fields until deployment. Unlike conventional weapons requiring fuel or triggers, antimatter annihilates on contact with normal matter, releasing tremendous energy while destroying itself. Just a single gram of antimatter can unleash an explosion comparable to a nuclear weapon fueled by roughly 90 kilograms of traditional material. In the relentless arms race on such a planet, stockpiles of antimatter weapons could accumulate. A single accident or hostile act might trigger a cataclysmic event. Day instantly turning to night, scorching winds ravaging cities, annihilating combatants and civilians alike. The aftermath would echo for centuries, a stark testament to the destructive power released when matter and antimatter collide. Yet remarkably, antimatter is all around us every day, existing naturally in cosmic rays and particle interactions, though safely scarce in our everyday environment. Now, let us embark on a cosmic thought experiment. What if the entire universe resembled an atom? The observable universe, vast and almost incomprehensible, may be just a tiny fragment of a far grander cosmos. Some theories suggest that the unobservable universe extends to a scale surpassing 20 trillion light-years in diameter. Despite such colossal dimensions, large swathes of this cosmic expanse might be largely empty, similar to the vast voids between atoms within matter. Matter itself, the foundation of all we know, is composed of innumerable atoms far too small for direct observation, even with the most advanced microscopes. Scientific evidence confirms that atoms consist of subatomic particles, protons, neutrons, electrons, and quarks. Intriguingly, some theories speculate that on a grander cosmic scale, the entire universe may itself function as an atom within an even larger structure. One such idea, the one-electron universe theory, proposes that all electrons are actually manifestations of a single particle moving back and forth in time, creating the illusion of multiplicity. Although this concept lacks strong scientific consensus, it sparks imagination and invites exploration of more substantiated notions. A more widely accepted framework is the multiverse theory, which posits that every atom, electron, and particle in our universe could correspond to an atom in a vastly larger cosmos. This concept expands our understanding of reality's complexity, urging us to contemplate endless possibilities beyond the confines of our observable universe. Science fiction often explores these ideas, imagining our universe as a tiny speck within a higher dimensional existence, or each atom containing entire alternate realities. Infinity becomes a central theme, suggesting that no matter how expansive our universe seems, it may be just one of an infinite array of universes. Observing the cosmos, we see a magnificent dance of minuscule particles building up to stars, planets, and living organisms. This raises a profound question. Could our entire universe be just a single component of something far more immense? This merging of the microscopic and macroscopic challenges us to withhold definitive judgments until a comprehensive theory of everything is developed, one that seamlessly unifies quantum mechanics and classical physics. According to current cosmological understanding, the universe began as an infinitely dense singularity before expanding in the monumental event known as the Big Bang. Everything we know originated from this unimaginably small point. However, it is important to differentiate this initial singularity from an actual atom, as it contained the fundamental elements that eventually gave rise to atoms and all matter. While these concepts may challenge our everyday understanding of reality, they encourage deep reflection on our place within the vast cosmic tapestry. Rather than diminish the wonder of existence, they enhance it. One leading candidate for a theory of everything is string theory, which envisions atoms not as solid spheres, but as vibrating strings. These vibrations give rise to all particles and forces in the universe, including gravity and quantum mechanics. Despite its elegance, string theory faces challenges, especially in explaining dark energy, a mysterious component that comprises a large part of the universe but remains poorly understood. Recently, researchers at Uppsala University in Sweden proposed a variation of string theory, suggesting that our universe resides on the edge of an ever-expanding cosmic bubble. Within and beyond this bubble, unknown dimensions may exist, and dark energy could be the result of interactions from this larger cosmic environment. If this unconventional view proves correct, it would revolutionize our scientific understanding and highlight humanity's infinitesimal role within a vast, complex, and largely incomprehensible cosmic structure. It is important to recognize that this idea functions as a thought experiment, a captivating way to reflect on our place within the vast cosmic expanse. Even if our perspective is limited and our understanding incomplete, the potential insignificance of our existence from an alternative viewpoint does not diminish its inherent value. Now let us ponder a timeless question. What becomes of your atoms after you die? Throughout human history, more than 100 billion people have passed away. According to the law of conservation of matter, which states that matter can neither be created nor destroyed, these atoms must still exist in some form. An intriguing possibility is that the atoms of those who have departed have not vanished, but instead have become part of you, the world around us, and are currently on an extraordinary journey across the universe. Exploring this concept reveals fascinating ways in which this transformation unfolds. The human body is a complex composition, approximately 60% water, 20% fat, 15% proteins, 2% carbohydrates, 2% salts and minerals, and about 1% other elements such as oxygen gases and vitamins. Most molecules in our bodies are water. Upon death, this water begins to change. It either evaporates into the atmosphere or seeps into the ground. The rate of this process depends on environmental factors like temperature and humidity. Even if the water remains liquid, it eventually becomes part of Earth's water cycle, evaporating, forming clouds, and returning as rain. Much of this rainwater flows into rivers and lakes, becoming part of the water we drink. Your body uses this water for countless functions, maintaining cells, regulating temperature, and supporting life processes. Some of this water is absorbed by plants, playing a crucial role in photosynthesis, the process by which plants convert water, carbon dioxide, and sunlight into carbohydrates and oxygen. The oxygen produced is breathed in by all living beings, including you. Meanwhile, the carbohydrates synthesized become vital nutrients for animals and humans, connecting the atoms of your departed loved ones to your own existence through this endless cycle. This illustrates the profound interconnectedness of life and the perpetual journey of atoms through various forms and functions. Delving deeper into the fate of atoms, consider metabolism. When you consume carbohydrates from plants, a complex exchange occurs. Your body produces carbon dioxide and water, substances plants rely on to thrive. This cyclical exchange underpins the continuous flow of matter and energy in the biosphere. Beyond water, the fate of your soft tissues, made of carbohydrates, fats, and proteins, is equally fascinating. These tissues are broken down by roughly 100 trillion bacteria residing in your body, particularly in your gut. During life, your immune system keeps these bacteria in check, but after death, the immune defenses cease, allowing bacteria to metabolize your tissues. This process is akin to a slow combustion, where bacteria digest your body's molecules, converting them into water, carbon dioxide, and various gases. Proteins, for instance, release nitrogen oxides and ammonia. Remarkably, some of these gases, like nitrogen oxides, are potent greenhouse gases, about 300 times more effective at trapping heat than carbon dioxide, highlighting the environmental impact of these biochemical cycles. As oxygen becomes scarce during decomposition, anaerobic bacteria, those that do not require oxygen, take over. They produce gases such as methane, hydrogen sulfide, and ammonia. These gases contribute to the characteristic doors of decomposition and also act as greenhouse gases, influencing the atmosphere. So, the next time you notice a faint, unusual scent outdoors, it's possible that you are inhaling atoms once part of your ancestors. Additionally, elements from decomposed bodies enter the soil, enriching it with nitrogen, phosphorus, potassium, magnesium, and other nutrients that act as natural fertilizers, supporting plant life and local ecosystems. Now, consider cremation as an alternative process. The intense heat transforms most atoms in the body, hydrogen, carbon, nitrogen, oxygen, sulfur, into gases such as water vapor, carbon dioxide, nitrogen oxides, and sulfur oxides released into the atmosphere. The remaining matter forms ashes, weighing approximately as much as you did at birth. These ashes primarily consist of phosphate and calcium, reflecting the composition of your bones. Eventually, these minerals enter the soil and become part of plants, which may be consumed by animals and humans, thereby recycling elements of your physical being through the web of life. In this way, fragments of you could literally become part of the food eaten by your descendants, allowing you to persist in a tangible sense. However, there is an important exception. Your body contains trace amounts of radioactive elements. These undergo radioactive decay, transforming into other elements before joining the biosphere. For example, radioactive potassium may decay into calcium, and elements like thorium and uranium will eventually turn into lead. During these decay processes, helium atoms are produced, some of which escape Earth's weak gravitational pull, drifting into space, while others may be captured by massive celestial bodies such as the Sun and Jupiter.
This intricate interplay of atoms and their transformations adds complexity to the cosmic journey of matter, highlighting the dynamic and ongoing nature of the universe.
Many atoms that once composed your body embark on extraordinary voyages beyond our solar system, drifting through space and venturing into the cosmos. These atoms continue moving indefinitely, transcending time itself. This leads to a profound question: do atoms last forever? Though life on Earth seems stable and predictable, governed by tides, daily sunlight cycles, and seasonal changes, the broader cosmos is a dynamic theater of continual change. Every day, millions of stars are born and others die. Even our Sun will eventually exhaust its nuclear fuel and transform into a red giant, causing Earth's environment to become inhospitable to life. After a few billion more years, the Sun will shed its outer layers and fade into darkness. This cosmic truth reveals that nothing in the universe is truly eternal, or is it? Atoms, the fundamental building blocks of matter, form the fabric of everything we know. When considering the end of our personal existence, it is crucial to understand that these atoms do not simply disappear. Instead, they undergo profound transformations, breaking down and reintegrating into ecosystems, beginning new cycles of existence. In simpler terms, the atoms that once made up our bodies persist long after we are gone. But how long can atoms last? Is there a point at which they cease to exist? To answer this, we must explore the deeper nature of atomic stability and cosmic time. To understand this fully, we need to explore the inner structure of atoms. Atoms consist of protons and neutrons at their core, surrounded by a cloud of electrons. The stability of an atom depends on the delicate balance between the number of electrons and protons. The atom's identity is determined by its atomic number, the count of protons it contains. For example, helium, which sits second on the periodic table, has 2 protons, giving it an atomic number of 2. While the number of neutrons in an atom is usually constant, exceptions occur. If an atom has an incorrect number of neutrons, it becomes unstable, much like losing a sock in the laundry. This instability often leads the atom to shed subatomic particles, sometimes releasing an electron and causing internal changes. Heavy atoms can spontaneously break down into smaller particles through a process called radioactive decay. This decay happens randomly, making it difficult to predict exactly when an atom will disintegrate or emit particles. However, statistical methods allow us to estimate the average time it takes for half of the atoms in a given sample to decay. This period is called the half-life. Atoms generally continue this emission of particles until they reach a state where their half-life becomes so long that they are effectively stable. Take bismuth-209, for instance. It undergoes alpha decay, but has a half-life more than 1 billion times longer than the estimated age of the universe, showcasing just how enduring some atoms can be. Because of this, bismuth-209 is often regarded as practically eternal. Yet the idea of true eternal life for subatomic particles opens up fascinating questions, especially regarding proton decay, a theoretical type of radioactive decay. One proposed model, the Georgi-Glashow theory, suggests that protons might transform into a positron and a neutral pion, with the pion further decaying into gamma-ray photons. It is crucial to highlight, however, that no experimental evidence has yet confirmed proton decay. Ongoing research at major laboratories worldwide aims to explore this mystery. Through a combination of scientific rigor and a bit of luck, future discoveries may illuminate this phenomenon and reshape our understanding of eternal existence at the subatomic level. From the birth of stars in the vast sky to tiny particles quietly fading away, the universe presents an elegant dance of creation and destruction. At the heart of this cosmic ballet, atoms persist, evolving slowly over immense stretches of time, linking the past, present, and future. As we contemplate atoms that might endure forever and wrestle with the elusive idea of true eternal life, the universe challenges us to think simultaneously about the very small and the unimaginably vast. In this ongoing dance of particles, we glimpse humanity's search for meaning, what it means to live, to last, and to exist. These silent, minuscule atoms carry the story of everything, reminding us that all things have beginnings and eventual ends. Yet, within this cycle of formation and decay lies a profound beauty, a connection that binds us to the cosmos. The atoms within us have witnessed ancient times, stars, and galaxies. They have been part of the universe's ever-changing dance, a dance without end, beyond the limits of time and space. As we journey through the immense reaches of the universe and the tiny realm of atoms, let us appreciate the interconnectedness of all things. In the dance of these tiny particles, we find echoes of our own brief existence, reminding us that, like atoms, we are woven into the grand story of the cosmos, unfolding over unimaginable spans of time.
Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.